एवरीवन और इस नए एक्सप्लेनर में आपका स्वागत है। आज हम एक बहुत ही इंपॉर्टेंट थ्योरम का एग्जैक्ट स्टेप बाय स्टेप प्रूफ कवर करने वाले हैं। मोनोटॉनिक f plus continuous alpha implies f in shoppers of alpha. I mean, if you're a university math student, you already know this is an absolute classic और एग्जाम्स के लिए तो ये सुपर इंपॉर्टेंट है। We're going to follow the exact notes step by step. तो चलिए बिना किसी डिले के शुरू करते हैं।
Okay, let's just quickly look at our roadmap for today. First up, 1, theorem and key idea. Then 2, proof steps 1 to 4. Moving on to 3, proof steps 5 to 7, and 4, proof steps 8 and 9. We'll wrap up with 5, flowchart walkthrough, and 6, important points and memory.
All right, here we go. What you're seeing right now is page 1 of our exact notes setting up the theorem. हम इन्हीं notes को closely follow करेंगे to ensure absolute precision. एक-एक detail हम exactly यहीं से read करेंगे.
Section 1, theorem and key idea.
Okay, let's read the exact theorem statement first. If f is monotonic on the closed interval from a to b, and if alpha is continuous on a to b, then f is an R of alpha. Or, exams mein, kabhi-kabhi it's asked like this. If f is monotonic on a to b and alpha is a continuous and monotonic on a to b, show that f is an R of alpha on a to b. So, iska meaning kya hai in simple words? Dekhiye, if f is always increasing or always decreasing, basically monotonic, on a to b and alpha is continuous, and let's say increasing, then the Riemann Stieltjes integral from a to b f d alpha exists. In short, and this is the big takeaway, monotonic f plus continuous alpha implies f in R of alpha. Yehi hamara ultimate proof goal hai aaj ka.
Before jumping into the math, is Porter proof का key idea समझना बहुत ज़रूरी है. First, since alpha is continuous, we can choose the partition so that every delta alpha I is very small, right? Second, since f is monotonic, on each subinterval xi minus 1 comma xi, the oscillation mi minus mi is easy to compute as f of xi minus f of xi minus 1, assuming f is increasing. Because of these two things, then u of p minus L of p becomes very small and can be made less than any given epsilon greater than 0. Continuity or monotonicity यहाँ एक साथ मिलकर magic create करते हैं, pulling the upper and lower sums infinitely close.
Moving right along, section 2, proof steps 1 to 4. Let's get into the formal proof.
Step 1. Let epsilon greater than 0 be given. We shall prove that u of p, f, alpha minus L of p, f, alpha less than epsilon for some partition p of the closed interval a, b. By Theorem 2.2, the integrability criterion, this will imply f and f sure R of alpha. Basically, हमें बस ये दिखाना है कि upper or lower sums का difference हमारे epsilon से छोटा है. Now, step 2. Since alpha is continuous on a, b, it must take all values between alpha of a and alpha of b. You'll see a note here. Continuous function on a closed interval is bounded and takes every intermediate value. Yet हमारा intermediate value theorem का direct application है, and it's absolutely crucial for setting up our partition.
All right, step 3. Also, alpha is monotonically increasing on AB. Hence, for any positive integer n, there exists a partition P of AB such that delta alpha I is equal to alpha of B minus alpha of A over n, for I equals 1, 2, 3, 4, 5, n, where delta alpha I equals alpha of xi minus alpha of xx minus 1. Quick note, this is possible since alpha is continuous and increasing. हमने completely equally spaced delta alpha I बना लिया है यहाँ पर. Then step 4. Let f be monotonically increasing on AB. The case of decreasing is similar. Then, in each delta xi equals xi minus 1, xi. The lower and upper bounds are mi equals of xi minus 1, mi equals of xi, ni equals 1, 2, 3, 4, n. Now what's really interesting about this slide is exactly how we set up those bounds. क्योंकि f strictly increasing है, interval के left side per exact minimum है, or right side per exact maximum. It's that simple.
Section 3, proof, steps 5 to 7. Let's do some algebra.
We are now looking at page 2 of our notes. We're just continuing the algebraic proof right from where we left off.
Okay, step 5. By definition of upper sum and lower sum, u of p f alpha minus L of p f alpha equals sum I equals 1 to n, bracket mi minus mi delta alpha I, where delta alpha I equals alpha of xi minus alpha of xi minus 1 greater than 0. Now in step 6, हम exactly वही substitution करेंगे जो हमने पहले set किया था.
Substitute mi equals f of xi and mi equals f of xi minus 1, तो हमारी इक्वेशन क्या बनेगी? U of p f alpha minus L of p f alpha equals sum I equals 1 to n, bracket f of xi minus f of xi minus 1, delta alpha I. Or क्योंकि delta alpha I a constant है, we can pull it completely outside the sum. So that equals alpha of b minus alpha of a over n, sum I equals 1 to n, bracket f of xi minus f of xi minus 1. याद रखिए, ये तभी possible हुआ since delta alpha I equals alpha of b minus alpha of a over n for all I. ध्यान से देखिए, हमने बस clever substitution use किया है यहाँ.
Now step 7. Guys, this is where the absolute magic happens. Use the telescoping or cancellation property, summation I equals 1 to n flat of xi minus flat of xi minus 1. अगर हम इसको expand करें, it becomes fi1 minus fe nonna plus fe side 1 minus fe2 plus dot 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 plus fin minus 1. Notice कर रहे हैं आप, सारे adjacent terms आपस में cancel out हो रहे हैं. बीच का सब कुछ कट जाएगा and we are left with just the very first and last terms fxn minus fx nonna, which is exactly f of b minus f of a. Therefore, हमारा expression बन जाता है upf alpha minus lpf alpha equals the alpha b minus alpha ever n ff minus fa. It's a beautiful simplification, and honestly, this cancellation is the true mathematical heart of the proof.
We're almost there. Section 4, proof steps 8 and 9. Let's wrap up the logic.
Step 8. Since alpha of b minus alpha of a and f of b minus f of a are fixed numbers, as n tends to infinity, that fraction alpha of b minus alpha of a upon n tends to 0. Hence, for sufficiently large n, u of p phi alpha minus L of p phi alpha is less than epsilon. हमने अपना main goal perfectly achieve कर लिया. Now, Step 9. By Theorem 2.2 integrability criterion, if u of p phi alpha minus L of p phi alpha is less than epsilon, there exists a partition P of closed interval AB such that the difference of upper sum and lower sum is less than any given epsilon greater than 0, therefore f in re are alpha. And with that, hence proved, हमारा complete formal proof यहाँ exactly conclude होता है.
Section 5. Flowchart walkthrough. Let's map it all out visually.
तो टॉप बॉक्स नंबर 1 से शुरू करते हैं. f is monotonic on a, b, alpha is continuous on a, b. यहाँ से अगला लॉजिकल स्टेप बॉक्स 2, choose partition so that delta alpha I is equal to alpha b minus alpha a upon n. फिर हमारी exact bound conditions बॉक्स 3. If f is increasing, mi is equal to f of xi minus 1, mi is equal to f of xi. और इन सब को कंबाइन करके we get box 4, u minus L is equal to summation mi minus mi delta alpha I, which equals alpha b minus alpha a upon n summation f of xi minus f of xi minus 1. देखा आपने कैसे फ्लो बिल्कुल स्मूथ है. आगे बढ़ते हैं. Next box directly points out telescoping sum gives summation f of xi minus f of xi minus 1 is equal to f of b minus f of a. इसको substitute करके अगले बॉक्स में we get u minus L is equal to alpha of b minus alpha of a into f of b minus f of a going to 0 as n tends to infinity, जिसके वजह से next box says u minus L is less than epsilon for large n. And finally, by Theorem 2.2, this perfectly implies f in alpha r. Honestly, this flowchart is a lifesaver for exam revision.
And finally, Section 6, important points and memory.
So the crucial point is really how you remember these properties. Here are the 5 important points to remember, read exactly from the notes. 1. Monotonic function implies easy identification of mi and mi. एकदम direct upper और lower bounds मिल जाते हैं. 2. Telescoping sum, summation I equal to 1 to n fxi minus fxi minus 1 is equal to fb minus fa. ये calculation का main shortcut था. 3. Continuity of alpha allows partition so that each delta alpha I is equal and can be made arbitrarily small. 4. The result holds for both increasing and decreasing f. Flexibility है यहाँ. And 5. This theorem gives a sufficient condition for integrability. Note कीजिएगा, strictly sufficient, not necessary.
And to formally wrap it all up, हमारी quick memory line. Monotonic f, which means no oscillation, plus continuous increasing alpha, which means small delta alpha I is possible, implies that upper and lower sums become close, which ultimately implies f in short r of alpha. अगर आप बस ये एक line deeply समझ गए, the whole proof just clicks into place. अब सोचने वाली बात यह है, just a thought exercise. अगर f बिल्कुल continuous हो और alpha purely monotonic हो, तो क्या ये integrability rule तब भी apply करेगा? Absolutely something deep to chew on. Thank you so much for joining me for this explainer. Keep practicing those proofs, and I'll catch you in the next one.